Let's prove Liouville's theorem. Recall that we defined all of the generalized coordinates as a configuration space. In other words, it's a space that uniquely defines position of the system, and it is n-dimensional. Now with Hamiltonian mechanics, we have coordinates and momenta, which is known as the phase space. And now it has dimensions of 2 times n. So let's consider a case where we look at the motion in the phase space. And we will consider scenario in which we have a swarm of particles. So lots of particles that move in the phase space. Let me show one projection of the phase space. So we'll have P sub I and Q sub I. The point Q sub I, P sub I, and we will look at a rectangular volume or element in the phase space. Phase space density will be defined, like we said, it's going to be whatever number of particles we have, so it's a swarm of particles, divided by the volume. So the volume, of course, is going to be just the product of dq sub 1 all the way to dq sub n, dp sub 1, dp sub n. We would like to watch this volume and figure out how this phase space density rho is changing. So phase space density is a function of time, obviously, but it's also defined in the phase space. So it's defined as a function of coordinates and momentum. So back to our little graph here. This element on the left is dp sub I. That's the height of this rectangle. The base of this rectangle will be dq sub I. We are looking at a small changes in both position and momentum. We can consider what happens to the particles that move in this volume of phase space. For example, let's say that particles that are moving into this rectangle from the left-hand side, they will be given by a rate of change of coordinate q sub I. Likewise, the flux of particles that comes from bottom will be given by the rate of change of momenta p sub I. So in other words, the particles that are flowing in inside this volume will be proportional to the overall density. I'm now only considering these two sides here. So the left side and the bottom side of this rectangle. These are the directions of particles flowing in. If they are flowing out, it doesn't matter because we are just defining the sign convention. So particles flowing in from the bottom will be given by rho times pi dot and times the size of this rectangle, the width of it, dq sub I. Then particles flowing from the left will be, again, proportional to the overall density times rate of change in coordinate, q sub I dot, and times the size of this rectangle, dp sub I. Or we can rearrange it, phase space density at this point times q sub I dot, dp sub I plus p sub I dot dq sub I. Next, we have to consider the flowing out of the particles. So these two sides of the rectangle. So now for particles flowing out. So for particles flowing out, let's first consider the top, this side here. We have to multiply the length of the side times the new rate of flow in that direction times the new phase space density that corresponds to this top side of the rectangle. So which becomes density times p dot sub I. That's very much what we got at the bottom, but that's not now the true value. The true value is now updated. We are taking the first term in the Taylor expansion and it will be a partial derivative with respect to p sub I because we're only considering motion that's along the direction of p sub I. And then we have density times pi dot, and then times the size of the element dpi. So that's as far as the top side. Now, as far as the right side, we'll have the second term, dp sub I, and again, we will have rho times q dot sub I, but that's not, again, the true value. We have to update it, and we update it by adding the Taylor term correction, d dq sub I, partial derivative of rho times qi dot, and times dq sub I. Now, next, what we're gonna do, we're gonna subtract the number of particles that we found flowing in minus the number of particles that we found flowing out. First, we'll see that these terms here are gonna cancel. This term here is gonna cancel this term here, as well as this term here is gonna cancel this term here. In other words, we have the same number of particles flowing in as flowing out, but other terms that involve partial derivatives are not going to cancel. So let's rewrite it. So we're going to get, just for one component so far, and we're going to get, with a minus sign, partial derivative of rho qi dot with respect to coordinate q sub I, plus partial derivative of rho pi dot with respect to pi component, right? And then we have the element sizes dqi and dpi. So this is the rate of flow. What is it equal to, this change in the rate of flow? Well, it's equal to partial derivative of rho with respect to time times dpi dqi. What I've written here is not quite right because I'm only considering one component. But of course, what I really have to do, I must sum over all of the dimensions. So sum over all I from 1 to n. And then, in fact, that overall sum will be equal to the rate of change, partial derivative of rho with respect to time. Let's rewrite it. Sum from 1 to n of partial derivative of rho. Now I'm opening these products with respect to q sub I times qi dot plus rho times partial derivative of q sub I dot with respect to q sub I plus partial derivative of rho with respect to momentum p sub I times p sub I dot, and plus rho times partial derivative of p sub I dot with respect to p sub I. So that's the sum. And together with a minus sign and the fact that it's going to be equal to the partial derivative of rho with respect to time, I simply add partial derivative of rho with respect to time, and this whole thing is now going to be 0. So this is what we have so far. This expression that involves density of particles in the phase space and a lot of partial derivatives. Couple of things to notice in this sum. First of all, we can factor out rho and these two terms here, this term and this term. So we're going to have rho, then we have partial derivative of qi dot with respect to q sub I, plus partial derivative of p sub I dot with respect to momentum p sub I. Okay? Here we want to recall Hamilton's equations that we derived last time. Qi dot is given by partial derivative of Hamiltonian with respect to the momentum p sub I, and then pi dot is equal to minus partial derivative of Hamiltonian with respect to coordinate q sub I. Okay. Note what we have inside this parenthesis. We can differentiate with respect to q sub I the first equation here, this guy. And what are we going to get? We're going to get a mixed derivative, partial derivative, that reads mixed derivative of Hamiltonian with respect to coordinate q sub I and momentum p sub I. And likewise, for the second term, differentiating the second equation, we're going to get the same mixed derivative. Now with the minus sign, so it's going to be minus mixed derivative of Hamiltonian with respect to q sub I and p sub I. So in fact, this term here is 0 due to Hamilton's equations. Therefore, the whole expression for the density of the phase space is simplified. Now we'll simply have sum from I equal 1 to n, partial derivative of the phase space density with respect to coordinate q sub I, times q sub I dot, plus partial derivative of phase space density with respect to p sub I times p sub I dot, and plus partial derivative of phase space density with respect to time, and that is equal to 0. We know that the phase space density is a function of all of the coordinates, all of the momenta, and time. In fact, what we got here is just the chain rule of the full derivative of the phase space density. So this here is therefore simply full derivative of rho with respect to time, which is equal to 0. So thus we proved that the phase space density is a constant, or phase space density behaves as incompressible fluid in phase space.